Hello there. Welcome to the Tranquil Tales channel. I'm so glad that you found your way here. Whether your day was long or you enjoy falling asleep in deep thoughts. Tonight we will take a journey through thunderstorms in different areas of the world, allowing your mind to rest and let the weight of gravity fall. Tonight we are not just floating through the storm, we are floating through rain and thunder to a restful deep sleep. A journey through thunderstorms. The gathering. Close your eyes and imagine you're somewhere safe and warm, watching through a window as the sky transforms. The air has changed. You noticed it hours ago, that particular heaviness, the way the afternoon light turned golden and strange. A thunderstorm is coming, and its story began long before the first drops fell. Let's drift back to the beginning to understand how these magnificent atmospheric events come to be. Every thunderstorm starts with something simple: warm, moist air rising. As the sun heats the Earth's surface throughout the day, pockets of air warm up and become lighter than the air around them. Like a hot air balloon, they begin to rise, lifting moisture with them into the cooler atmosphere above. This rising air, called an updraft, is the engine of every thunderstorm, sometimes reaching speeds of 100 miles per hour in the most powerful storms. As this warm air climbs higher and higher, something beautiful happens. The moisture it carries begins to cool, and as it cools, it condenses into tiny water droplets, millions upon millions of them clustering together. This is how clouds are born. The particular clouds that bring thunderstorms are called cumulonimbus clouds, towering giants that can stretch from as low as 1,000 feet above the ground all the way up to 50,000 feet or more, nearly 10 miles high. If you could see one from the side, it would look like an enormous anvil, with a flat top spreading out where it hits the upper atmosphere. Inside this cloud, a hidden world of activity unfolds. Water droplets collide and merge, growing heavier. Ice crystals form in the freezing upper reaches. Everything is in motion. Updrafts carrying material skyward, downdrafts pulling it back down. The cloud becomes a factory building the storm piece by piece. Now let's talk about what makes a thunderstorm truly remarkable: lightning. The secret lies in all that motion we just described. As ice crystals, water droplets, and small hailstones bounce against each other inside the storm cloud, they exchange electrical charges. The lighter ice crystals, carried upward by the updrafts, tend to become positively charged. The heavier particles that fall toward the bottom of the cloud become negatively charged. Gradually, the cloud separates into layers, positive charges gathering near the top, negative charges pooling at the bottom. The ground below, meanwhile, becomes positively charged in response, especially tall objects like trees, buildings, and towers. The stage is set. When the electrical difference becomes too great to resist, typically around 100 million volts, nature bridges the gap in a fraction of a second. That bridge is lightning. Here's something wonderful to contemplate as you relax. A single lightning bolt is only about 1 inch in diameter, but it can heat the air around it to approximately 50,000 degrees Fahrenheit. That's 5 times hotter than the surface of the sun. This extreme heat causes the air to expand so rapidly that it creates a shock wave, the thunder we hear rolling across the sky. The sound travels at the speed of sound, of course about 767 miles per hour, which is why we see the lightning first and hear the thunder moments later. You can actually estimate how far away a lightning strike occurred. Count the seconds between the flash and the thunder, then divide by 5. that gives you the distance in miles. Thunderstorms follow a life cycle like living things. Meteorologists recognize three distinct stages. First comes the developing stage, which we've been exploring, the cumulus cloud building upward, updrafts dominant, the storm gathering its strength. This stage typically lasts about 10 to 15 minutes. Then comes the mature stage when the storm is fully formed and most active. Rain falls heavily, lightning flashes frequently, and both updrafts and downdrafts exist within the cloud. This is when the storm is most intense, and it can last 30 minutes or longer. Finally, the dissipating stage arrives, when the updrafts weaken and downdrafts dominate. The storm begins to fall apart, the rain lessens, and the cloud gradually dissolves back into the atmosphere. Our planet experiences about 16 million thunderstorms each year. That means at any given moment, roughly 2,000 thunderstorms are occurring somewhere on Earth. Most of these are ordinary storms, what meteorologists call single-cell thunderstorms, brief, isolated events that develop, mature, and dissipate within an hour or so. As you listen to the rain against the window, as you feel yourself settling deeper into comfort and relaxation, consider this. The water falling from the sky might have been anywhere before this moment. It could have been part of an ocean, a river, a leaf, or even a cloud over a different continent. Water cycles endlessly through our atmosphere, and thunderstorms are one of nature's ways of redistributing it, bringing moisture from the seas to the land, nourishing everything below. The storm rumbles outside, powerful yet distant, a reminder that you are safe, warm, and sheltered. Let its rhythms carry you deeper into rest as we continue our journey through the world of thunderstorms. The elements. The storm has settled into its rhythm now, and so have you. Your breathing has slowed, matching the pace of the rain. Let's drift deeper into the mysteries of these atmospheric wonders, exploring the hidden details that make each thunderstorm unique. Think about the rain itself for a moment. Each raindrop that falls begins as something impossibly small, a microscopic particle of dust, salt, or pollen floating high in the atmosphere. Water vapor condenses around these tiny nuclei, building drop by drop. A typical raindrop is about 1 to 2 millimeters in diameter when it finally falls, but it didn't start that way. It began as a cloud droplet roughly 100 times smaller, and it had to collide and merge with about 1 million other cloud droplets to become large enough to fall as rain. Imagine that, 1 million tiny droplets coming together just to create one drop that taps against your window. The sound you're hearing, that soothing patter of rain, varies depending on what it strikes. Rain on leaves sounds different from rain on pavement, different from rain on water. But there's another sound that sometimes accompanies thunderstorms, the distinctive ping and clatter of hail. Hail forms in the powerful updrafts we talked about earlier, but its creation is more complex than you might imagine. A hailstone begins as a small ice pellet or frozen raindrop. As the updraft carries it high into the freezing upper portions of the cloud, it collects moisture, which freezes onto its surface in layers like an onion. If the updraft is strong enough, it can carry the hailstone up and down through the cloud multiple times, each journey adding another layer of ice. The largest hailstones require updrafts of at least 100 miles per hour to keep them aloft, which is why severe thunderstorms produce the biggest hail. The record for the largest hailstone in the United States was nearly 8 inches in diameter, about the size of a volleyball, and it fell in South Dakota in 2010. Let's return to lightning for a moment, because there's so much more to understand about these brilliant forks of electricity splitting the sky. While we see lightning as a single flash, what's actually happening is far more intricate. Most lightning begins with what's called a stepped leader, an invisible channel of charged air that zigzags down from the cloud in steps of about 150 feet at a time, branching and searching for the path of least resistance. This happens so quickly that our eyes can't perceive it. When the stepped leader gets close to the ground, a streamer of positive charge rushes up to meet it from the earth below. The moment they connect, a powerful electrical current surges upward along the channel. This is the return stroke, and it's what we actually see as the bright flash of lightning. The entire process, from stepped leader to return stroke, takes less than 1 second, but the channel can be used multiple times, which is why lightning often appears to flicker. Not all lightning reaches the ground, though. In fact, most lightning stays within the clouds. Cloud-to-cloud lightning, or intra-cloud lightning, accounts for about 75% of all lightning strikes. These are the flashes that illuminate the clouds from within, creating that soft, diffuse glow that lights up the night sky. Some people call this sheet lightning, though it's really just regular lightning happening inside or between clouds, hidden from direct view. It's gentler on the eyes than cloud-to-ground lightning, like a lamp behind a curtain, and it's equally beautiful in its own quiet way. Thunder itself deserves more of our attention as you settle deeper into relaxation. We mentioned earlier that thunder is caused by the rapid expansion of air heated by lightning, but the sound is more complex than a simple boom. The rumbling, rolling quality of thunder, the way it seems to move across the sky and fade slowly, happens because sound waves from different parts of the lightning bolt reach your ears at different times. A lightning bolt might be several miles long, stretching from cloud to ground or across the sky. The sound from the nearest part reaches you first, followed by sound from progressively farther sections. Additionally, sound waves bounce off clouds, hills, and buildings, creating echoes that extend and deepen the rumble. This is why thunder from a distant storm sounds like a low, sustained roll, while thunder from a nearby strike is a sharp crack. The speed of sound being what it is, about 1 mile every 5 seconds, means thunder is rarely heard from more than 10 to 15 miles away, even from powerful storms. As you lie here, safe and comfortable, imagine the scale of what's happening in a thunderstorm. The amount of energy involved is staggering. A typical thunderstorm releases the energy equivalent of a 20 kiloton nuclear bomb, about the same size as the bomb dropped on Nagasaki, but this energy is released gradually over the storm's lifetime rather than all at once. Much of this energy goes into lifting and moving air, condensing water vapor, and generating lightning. A single lightning bolt, despite its power and brilliance, contains about 1 billion joules of energy, enough to power a 100-watt light bulb for about 3 months. Yet the storm produces many such bolts, along with rain, wind, and all the other phenomena we associate with thunderstorms. The air itself changes during a thunderstorm in ways you might have noticed. That fresh, clean smell that often comes with or after rain, especially noticeable after a dry spell, has a name: petrichor. It comes from oils that plants release during dry periods, which accumulate on rocks and soil. When rain falls, these oils are released into the air along with a compound called geosmin, produced by soil bacteria. Together, they create that distinctive earthy scent. But there's another smell associated with thunderstorms: ozone. Lightning splits oxygen molecules in the air, and some of these recombine into ozone, which has a sharp, clean, almost electric smell. If you've ever noticed a crisp, tangy scent during or after a thunderstorm, you were smelling ozone molecules created by lightning drifting down from the sky. The storm continues its work outside, moving through its natural cycle, distributing water across the landscape, cleaning the air, balancing electrical charges between earth and sky. And you continue your own cycle, moving deeper into rest, your mind calm, your body relaxed, carried along by the rhythm of rain and the distant conversation of thunder. Let the storm sing you to sleep. The dance of air and water. You're drifting now, floating on the sounds of the storm, and that's exactly where you should be. Let's wander further into the world of thunderstorms, discovering the quiet wonders that unfold in the darkness, in the clouds, in the spaces between lightning and thunder. There are places on Earth where thunderstorms are more common than others, where the conditions align so perfectly that the sky rumbles almost every day. The place that holds the record for the most thunderstorms is Lake Maracaibo in Venezuela. This lake experiences storms an average of 260 nights per year. That's more than 70% of all nights. The phenomenon even has a name, Catatumbo lightning, named after the river that feeds the lake. The unique geography creates the perfect conditions. Warm, moist air from the Caribbean meets the cool air descending from the Andes Mountains, and surrounded by the lake's waters, storms form with remarkable reliability. Some nights, the sky flashes with lightning up to 280 times per hour, creating a natural light show that has guided sailors for centuries. Closer to home, Florida holds the title for the most thunderstorms in the United States, with areas near Tampa and Orlando experiencing thunder on 80 to 100 days each year. The peninsula's geography creates what meteorologists call a sea breeze convergence zone. During summer afternoons, sea breezes blow inland from both the Atlantic Ocean and the Gulf of Mexico. These breezes meet in the middle of the state, forcing warm, humid air upward, triggering the development of towering thunderstorms almost like clockwork. If you've ever been to Florida in summer, you know this rhythm. Mornings start clear and hot, and by afternoon the sky darkens and the storms roll in. Let's think about the wind for a moment, because thunderstorms don't just bring rain and lightning, they bring movement to the air itself. Every thunderstorm creates its own wind patterns. As rain falls and pulls cool air down with it, this creates what's called a downdraft. When this column of cool, dense air hits the ground, it spreads outward in all directions like water from a fountain. This spreading wind is called an outflow, and it's what you feel as that sudden cool breeze that arrives just before the rain. Sometimes this outflow is strong enough to cause damage. Straight-line winds from thunderstorms can reach 100 miles per hour or more, rivaling the winds of a tornado but spreading out in a line rather than rotating. These powerful outflows are called downbursts, and when they're especially strong and concentrated, they're called microbursts. A microburst typically affects an area less than 2.5 miles across and lasts only 5 to 15 minutes, but it can be devastating, snapping trees and damaging buildings. Now imagine the interior of a thunderstorm cloud again, that hidden realm of ice and water and motion. Within the most powerful storms, the ones called supercells, the updrafts and downdrafts become so organized that they can persist for hours rather than minutes. A supercell thunderstorm is relatively rare, accounting for only about 1% of all thunderstorms, but they're responsible for most of the severe weather events we hear about: large hail, damaging winds, and the strongest tornadoes. What makes a supercell different is the presence of a rotating updraft called a mesocyclone. This rotation happens when winds at different altitudes blow at different speeds and directions, a phenomenon called wind shear. The spinning column of air can be 2 to 6 miles in diameter and is so powerful that it can sustain the storm for many hours, sometimes traveling hundreds of miles. Lightning has another secret to share with you as you rest here in the darkness. While most lightning appears white or blue-white, lightning can actually take on different colors depending on what's in the atmosphere. Red lightning can occur when lightning passes through rain, which scatters the light. Blue lightning is common and comes from the lightning itself in clear air. Yellow or orange lightning suggests the presence of dust in the atmosphere, common in dry regions or during droughts. Green lightning is rare but can happen when light passes through hail or when there's a high concentration of oxygen in the air. Each storm paints with slightly different colors, a palette created by the unique mixture of elements present that day in that place. Water droplets in a cloud are incredibly small, typically around 10 to 15 micrometers in diameter, which is about 1/5 the thickness of a human hair. They're so small and light that the gentlest updrafts can keep them suspended indefinitely. In fact, these tiny droplets fall at a speed of only about 1 centimeter per second, so slowly that a cloud droplet would take 12 hours to fall from a cloud just 1,500 feet high, except it would evaporate long before reaching the ground. This is why clouds don't just fall out of the sky, even though they contain enormous amounts of water. A small cumulus cloud, the kind you might see on a pleasant afternoon, contains about the same amount of water as an Olympic-sized swimming pool, roughly 500,000 pounds of water suspended in air. Speaking of the weight of water, let's consider what falls during a thunderstorm. A moderate rainstorm might drop about 1 inch of rain over a given area. That might not sound like much, but 1 inch of rain falling over 1 square mile amounts to about 17 million gallons of water, weighing approximately 143 million pounds. A typical thunderstorm might cover 15 square miles and drop 2 inches of rain, which means it's releasing over 500 million gallons of water, more than 4 billion pounds, back to the earth below. All of that water was lifted into the sky, drop by microscopic drop by the power of rising warm air. And now it returns, completing its cycle, nourishing the ground, filling streams and rivers, soaking into soil where plant roots can reach it. There's a type of lightning that most people never see, but it's among the most spectacular: sprites and jets. These are electrical phenomena that occur above thunderstorms, reaching up toward space rather than down toward the ground. Sprites appear as brief, reddish flashes that extend from the tops of thunderstorms up to 50 miles into the upper atmosphere. They last only a few milliseconds and are so faint they're nearly impossible to see with the naked eye. Pilots flying at high altitudes are the ones who most commonly spot them. Blue jets are similar but appear as blue cones of light shooting upward from storm clouds. These upward lightning events were only discovered in recent decades, reminding us that even something as familiar as a thunderstorm still holds mysteries, still has secrets to reveal. The storm outside is doing what storms have done for billions of years: redistributing heat and moisture, balancing the atmosphere, renewing the earth. And you are doing what you need to do: resting, releasing the day, allowing yourself to drift on these sounds and stories into the deep, peaceful sleep that awaits. Let the thunder fade, let the rain carry you gently down. The Ancient Symphony. You're so deeply relaxed now, your mind floating like a leaf on water, and the storm continues to tell its story. Let's explore the deeper mysteries, the connections between thunderstorms and the world around them, the ways these atmospheric events shape our planet and our lives. Thunderstorms are ancient, far more ancient than humanity. Rain has been falling on Earth for billions of years, and lightning has been splitting the sky for just as long. But here's something remarkable to contemplate. Scientists believe that lightning may have played a crucial role in the origin of life itself. When lightning strikes, it has enough energy to break apart nitrogen molecules in the atmosphere and help them combine with oxygen to form nitrogen oxides. These compounds dissolve in rain and fall to the earth as nitrates, which are essential nutrients for plants. Some researchers estimate that lightning produces between 5 and 10 million tons of nitrogen compounds each year, naturally fertilizing the soil. In Earth's early days before life existed, lightning may have helped create the first complex organic molecules, the building blocks of life, through similar chemical reactions in the atmosphere. Long before weather forecasting, before satellites and radar, humans learned to read the signs of approaching storms. One of the most reliable signs is still one we can observe today: the behavior of air pressure. As a thunderstorm approaches, barometric pressure drops. This happens because the rising warm air at the center of the developing storm creates a region of lower pressure. The human body can sometimes sense these pressure changes. You might notice it as a headache, joint pain, or simply a feeling that something is coming. Animals are even more attuned to these shifts. Birds often fly lower before a storm because the lower air pressure makes it harder to fly at their usual altitudes. Cows tend to lie down in fields when they sense a pressure drop, perhaps seeking the driest spot before rain arrives. Even insects change their behavior. Bees return to their hives, and ants work more frantically to secure their colonies. The storm announces itself in 1,000 subtle ways to those who know how to listen. Thunder and lightning have captured human imagination across every culture and every age. The ancient Greeks believed Zeus threw lightning bolts from Mount Olympus. Norse mythology gave us Thor, whose hammer Mjolnir created thunder and lightning. The Romans worshipped Jupiter, whose symbols were the lightning bolt and the eagle. Indigenous peoples around the world developed their own understandings. The Navajo saw lightning as a manifestation of sacred power, while some West African traditions viewed thunderstorms as the voice of ancestors. These weren't simply superstitions. They were ways of acknowledging the awesome power of nature, the force that could split trees, start fires, and bring life-giving rain. In a way, the reverence was appropriate. A lightning bolt carries about 300 million volts and can heat the air to temperatures exceeding 50,000 degrees Fahrenheit, as we've discussed. Ancient peoples didn't know the science, but they understood the power. Let's drift into the question of where thunderstorms form most frequently on our planet. We've talked about specific locations, but there's a broader pattern. Thunderstorms need three basic ingredients: moisture, instability, and lift. This is why they're most common in tropical regions near the equator, where the sun's heat is most intense. The air is humid from nearby oceans and rising air is constant. Central Africa, the Amazon basin, and Southeast Asia all experience frequent thunderstorms. But altitude matters too. Mountainous regions create their own weather. As air is forced up and over mountains, It cools and condenses, often triggering storms. The Rocky Mountains in North America, the Andes in South America, and the Himalayas in Asia all experience regular thunderstorm activity during certain seasons. Interestingly, the world's oceans, despite having abundant moisture, experience relatively few thunderstorms compared to land. This is because water heats up and cools down much more slowly than land, so it doesn't create the strong temperature contrasts and rapid heating that trigger storm development. Within a thunderstorm, raindrops fall at different speeds depending on their size. Small drizzle drops, less than half a millimeter across, fall at about 2 meters per second, a gentle drift. Large raindrops, around 5 millimeters in diameter, fall at roughly 9 meters per second, or about 20 miles per hour. But raindrops can't grow infinitely large. Once they reach about 6 millimeters in diameter, they become unstable. The air resistance flattens them out and eventually breaks them apart into smaller drops. This is why even in the heaviest downpour, raindrops remain relatively small. The terminal velocity, the maximum falling speed, is achieved when the air resistance equals the force of gravity pulling the drop down. It's a perfect balance, played out millions of times with every rainfall. Thunderstorms also play a vital role in regulating Earth's temperature. All that rising warm air and falling rain is part of a global heat engine. The equatorial regions receive more solar energy than the polar regions, and thunderstorms help redistribute this heat. When water evaporates, it absorbs heat energy from the surface. This water vapor rises in thunderstorm updrafts, carrying that heat high into the atmosphere. When the water condenses back into clouds and rain, it releases that heat energy into the upper atmosphere, where winds can carry it toward the poles. In this way, thunderstorms are part of the planet's air conditioning system, preventing the equator from getting hotter and hotter while the poles grow colder. Scientists estimate that the entire planet experiences about 100 lightning flashes every single second. That's 8.6 million lightning strikes per day, each one part of this great global system of energy transfer. There's a phenomenon called virga that you might have seen without knowing its name. Virga is rain that falls from a cloud but evaporates before reaching the ground. In dry climates, or when the air beneath a storm is particularly dry, the raindrops begin their journey downward but can't complete it. They evaporate in mid-air, creating beautiful streaks or wisps beneath the cloud, curtains of rain that never quite arrive. For someone standing below, the sky is dark with storm clouds, rain is clearly falling up above, but the ground remains dry. It's a reminder that not every storm completes its full cycle, that sometimes the journey matters more than the destination. Virga is especially common in desert regions, where the air is so dry that rain evaporates quickly, but it can occur anywhere when conditions are right. As you lie here, so comfortable, so relaxed, think about the water cycle one more time. Every raindrop that falls has been on a journey. Perhaps it was part of the ocean, drawn up by evaporation, carried by winds across continents, lifted into a towering thunderstorm cloud, frozen and thawed and frozen again, and finally released to fall as rain. After it reaches the ground, it might soak into the soil, be taken up by a plant's roots, be transpired back into the air through leaves, or flow into a stream and begin the journey back to the sea. The average water molecule spends about 9 days in the atmosphere before returning to Earth's surface, but the complete cycle from ocean to atmosphere and back again can take thousands of years. The rain you hear now might have fallen as snow on a mountain in ancient times, or been drunk by a dinosaur, or supported a forest that became coal. Water is patient, enduring, eternal. The storm outside is easing now, moving on to other places, other listeners. Its work here is nearly done. And your work, the work of rest, of release, of letting go, is well underway. Let these last sounds carry you deeper still into the peaceful darkness where dreams wait. Whispers in the wind. You're drifting deeper now, floating in that peaceful space between waking and sleeping, and the storm has become a lullaby, a gentle companion guiding you toward rest. Let's explore a few more secrets before you slip away entirely into dreams. There's something called St. Elmo's fire that sailors and pilots sometimes witness during thunderstorms. A beautiful, eerie phenomenon that looks like blue or violet flames dancing on the tips of masts, wings, or any pointed object. Despite its name, it's not actually fire at all. It's a corona discharge, a kind of continuous electrical glow that happens when the electric field in the atmosphere during a storm becomes strong enough to ionize the air around pointed objects. The charged particles in the air create a luminous plasma that glows with that distinctive blue light. This phenomenon has fascinated and sometimes frightened people for centuries. Sailors considered it an omen, sometimes good, sometimes bad. The name comes from Saint Erasmus of Formia, the patron saint of sailors, whose name was corrupted to Elmo over time. The glow typically appears just before or during thunderstorms and can persist for several minutes, casting an otherworldly light over everything it touches. Now let's think about the structure of a raindrop itself. We often draw raindrops as teardrop-shaped, pointed at the top, rounded at the bottom, but this isn't accurate. Small raindrops, less than about 1 millimeter across, are actually spherical, held in that perfect shape by surface tension. As raindrops grow larger, they begin to flatten on the bottom due to air resistance as they fall. Large raindrops, around 4 to 5 millimeters across, look more like hamburger buns, rounded on top with a flattened or even slightly concave bottom. The air pushes up against the falling drop, creating this distinctive shape. If you could freeze time and examine a raindrop mid-fall, you'd see this strange geometry, so different from what we imagine. It's a reminder that nature often defies our expectations, showing us beauty in unexpected forms. Thunderstorms don't just affect the weather at ground level, they create ripples that extend far into the upper atmosphere and even into space. When lightning occurs, it generates radio waves across a broad spectrum of frequencies. These electromagnetic waves, called radioatmospherics or spherics, can travel thousands of miles through the Earth's atmosphere and along the boundary between the Earth and the ionosphere. Radio operators and scientists can detect these signals from storms happening on the other side of the planet. In fact, there's a constant background of radio noise from the approximately 2,000 thunderstorms happening around the world at any given moment. This natural radio static was actually one of the first things detected when humans began experimenting with radio technology in the late 1800s. The storms were broadcasting their presence long before we knew how to listen. Let's drift back to hail for a moment because these ice stones have more to tell us. When hailstones are cut open, they reveal concentric rings, much like the rings in a tree trunk. Each ring represents a journey through the thunderstorm cloud, a trip up into the freezing zone where a new layer of ice formed, then a fall through warmer, wetter regions where water droplets froze onto the surface, then back up again for another cycle. By counting the rings, Scientists can estimate how many times a hailstone traveled up and down through the storm before finally becoming too heavy for even the strongest updrafts to hold. Some large hailstones show 10 or more layers, meaning they made that journey at least 10 times before falling to Earth. Each hailstone carries within it the biography of its storm, a frozen record of turbulence and power. There's a type of thunderstorm that forms in winter, which might seem surprising since we usually associate thunderstorms with hot summer days. These winter thunderstorms, sometimes called thundersnow events, are relatively rare but absolutely spectacular. They occur when the atmosphere is unstable enough and there's sufficient moisture, even in cold conditions. Instead of rain, these storms drop snow, sometimes very heavy snow, accompanied by lightning and thunder. The snow muffles the sound of thunder, so it typically can't be heard as far away as it would be in a summer storm. Thunder from a thundersnow event can usually only be heard within a radius of 2 to 3 miles from the lightning strike, compared to the 10 to 15 miles possible in normal conditions. The combination of heavy snow falling and the eerie light of lightning creates an almost surreal experience, as if the rules of weather have been momentarily suspended. Animals have evolved fascinating adaptations to deal with thunderstorms. Many birds can sense the drop in air pressure that precedes a storm by hours or even a full day, and they'll fly away from the storm's path or seek shelter. Some species, like golden-winged warblers, have been tracked evacuating an area up to 24 hours before a severe storm system arrived, traveling hundreds of miles to avoid it entirely. Elephants can detect the low-frequency rumble of thunder from storms more than 150 miles away, far beyond the range of human hearing. These infrasound waves travel through the ground as well as the air, and elephants sense them through their sensitive feet and trunks. In times of drought, elephants will follow these distant storm sounds toward rain and the fresh vegetation that follows. It's a remarkable navigation system, tuned to the voice of the weather itself. The tallest thunderstorm ever recorded reached an altitude of approximately 75,000 feet, more than 14 miles high, extending well into the stratosphere. This extraordinary storm occurred over the Pacific Ocean in 2018 and was measured by NASA satellites. Most thunderstorms tap out at around 40,000 to 50,000 feet, where they hit a layer of atmosphere so stable and warm that even the strongest updrafts can't penetrate it. But under exceptional circumstances, with extreme instability, powerful updrafts, and the right atmospheric conditions, a storm can burst through this barrier and grow even taller. These overshooting tops, as they're called, last only briefly before the updraft weakens and the cloud top collapses back down, but for those moments, the storm towers above almost everything else in the sky except the highest wisps of cirrus clouds. Consider the lifespan of a single water droplet within a cloud. It might exist as liquid water, then freeze into ice, then melt back to liquid, then evaporate into vapor, then condense back to liquid, all within the same storm system, all within the span of minutes. Each phase change involves energy. Heat is absorbed during evaporation and melting, heat is released during condensation and freezing. This constant cycling of water between phases, and the energy exchanges that come with it, is what powers the storm. The latent heat released when water vapor condenses into cloud droplets provides additional energy that strengthens the updrafts, allowing the storm to build even taller. It's a self-reinforcing system. The more water that condenses, the more heat is released, the stronger the storm becomes, the more water can be lifted and condensed. until eventually the balance shifts, the storm exhausts its fuel, and the dissipating stage begins. The storm has nearly passed now. Its thunder is just a memory, its rain barely a presence. You've traveled through the life of a thunderstorm, from its beginning to its end, from cloud formation to dissipation, from the first updraft to the last drops falling softly to earth. And in that journey, you've let go of the day, released your thoughts, allowed your body to sink into perfect, comfortable rest. The storm moves on as all storms must, and you move deeper into sleep, as peaceful as rain-washed air. The deep calm. You're so far into relaxation now, so close to sleep, and yet there are still gentle wonders to share, soft truths about these storms that will carry you the rest of the way into dreams. Let your mind float on these words like a boat on still water. There's a phenomenon meteorologists call a gust front, the leading edge of cool air that rushes out from a thunderstorm and spreads across the ground. If you've ever stood outside as a storm approached, you've felt it, that sudden rush of cool wind, the temperature dropping within seconds, the first scattered raindrops arriving moments later. This boundary between the cool storm air and the warm air it's pushing aside can be quite dramatic. The cool air, being denser, acts like a wedge, lifting the warm air ahead of it. Sometimes this lifting is strong enough to trigger new thunderstorms along the gust front, creating a line of storms marching across the landscape. On radar, these gust fronts appear as thin lines, called fine lines, even when there's no precipitation, because the turbulent air along the boundary creates detectable changes in wind patterns. The temperature difference across a gust front can be as much as 10 to 15 degrees Fahrenheit, arriving in less than a minute. Let's think about the colors of the sky during thunderstorms. We're all familiar with dark gray storm clouds, but sometimes thunderstorm clouds can appear green. This greenish tint has fascinated people for generations, and it's often associated with severe storms, particularly those capable of producing tornadoes or very large hail. Scientists believe the green color comes from a combination of factors. The way sunlight, particularly the reddish light of late afternoon, filters through the thick cloud, the presence of water and ice within the cloud, and the way our eyes perceive the contrast between the storm's darkness and the lighter sky around it. The exact mechanism is still debated, but the presence of large amounts of hail seems to enhance the effect. When you see that strange greenish cast to a storm cloud, it's worth paying attention. It often means the storm is particularly powerful. Lightning has a preferred path. While we think of lightning as striking randomly, it actually seeks out the easiest route to complete the electrical circuit. This is why lightning often strikes tall objects, trees, buildings, towers, mountains. The taller the object, the closer it is to the charged cloud base, and the shorter the distance the electrical discharge needs to travel. Lightning also prefers good conductors. Metal objects, wet wood, and water all conduct electricity well, making them more attractive to lightning than dry rock or rubber. This is why you should never stand under a tall tree during a thunderstorm. Trees, especially when wet, provide an excellent path for lightning to reach the ground. In the United States, lightning strikes the ground approximately 25 million times each year, though thanks to modern lightning detection networks, we can now track and count these strikes with remarkable accuracy. There's something called a mesoscale convective system, or MCS, which sounds technical but describes something you've probably experienced. An MCS is a collection of thunderstorms that organize into a larger system, often forming a line that can be dozens or even hundreds of miles long. These systems can persist for many hours, sometimes lasting through the entire night, bringing waves of rain and lightning. The storms within an MCS feed off each other. The outflow from one storm helps trigger the next, creating a self-sustaining system. One particular type of MCS is called a squall line, a line of intense thunderstorms that can produce damaging winds, frequent lightning, and heavy rain along a relatively narrow band. As these systems mature, they often develop a region of lighter, more widespread rain that trails behind the intense convection, called the stratiform region. This is where you might experience gentle, steady rain for hours after the main storm line passes. Water in the atmosphere exists in three phases: solid, liquid, and gas, and thunderstorms contain all three simultaneously. Ice crystals exist in the cold upper reaches. Supercooled water droplets float in the middle layers, remaining liquid even below freezing temperatures, and water vapor permeates the entire cloud. But there's a fourth state of water that exists briefly in thunderstorms. Supercooled liquid water droplets can exist at temperatures as low as -40 degrees Fahrenheit without freezing. These droplets are in an unstable state, and the slightest disturbance, contact with an ice crystal, an airplane passing through, even a speck of dust, can cause them to freeze instantly. This process, called contact nucleation, is one of the ways ice forms in clouds. Aircraft flying through regions of supercooled water can accumulate ice on their wings and fuselage very quickly, which is why pilots carefully avoid flying through certain parts of thunderstorms. The electricity in a thunderstorm doesn't just flow in one direction. While we usually think of lightning traveling from cloud to ground, there's also something called positive lightning, which originates from the positively charged top of the storm cloud rather than the negatively charged bottom. Positive lightning is less common, accounting for only about 5 to 10% of all cloud-to-ground strikes, but it's far more powerful. Positive lightning bolts carry up to 10 times the electrical current of negative lightning and can strike from the anvil of a storm, which may be miles away from where rain is falling. This is where the phrase "a bolt from the blue" comes from. Positive lightning can strike from a clear sky, seemingly out of nowhere from a storm that appears to be far away. These strikes are more likely to cause fires and damage because of their higher energy. Thunderstorms play a crucial role in cleaning the atmosphere. Rain falling through polluted air acts like nature's scrubber, washing dust, pollen, pollutants, and particles out of the air. This process, called wet deposition, is one of the main ways the atmosphere cleanses itself. After a thunderstorm passes, the air often smells fresh and clean, and it actually is cleaner. Studies have shown that rainfall can reduce particulate matter in the air by 30 to 50% or more, depending on the intensity of the rain. Even the wind from thunderstorms helps by mixing and dispersing pollutants. The violent turbulence within a thunderstorm can transport air from ground level to the upper atmosphere in minutes, redistributing everything it contains across vast regions. Finally, let's consider one more beautiful truth about thunderstorms. Every storm is unique. No two are exactly alike. The specific combination of temperature, humidity, wind patterns, geography, and countless other factors means that each thunderstorm has its own character, its own story. The storm you're listening to now, whether real or imagined, exists in this moment and will never occur again in quite this way. The particular arrangement of water molecules, the exact path each lightning bolt takes, the precise rhythm of the rain, all of it is singular, unrepeatable. Like snowflakes, like fingerprints, like the moment you're experiencing right now as you drift towards sleep. The storm has given you everything it has, its sounds, its secrets, its ancient rhythms. And now it releases you into sleep, into the deep rest that waits beyond words, beyond thought. The thunder has faded to memory. The rain has become silent. And you float free, peaceful, safe. Let it go now. Let the last whispers carry you down into the soft darkness. The final whispers. You're floating now, nearly dreaming, but before you slip away completely, let these last gentle truths about thunderstorms settle over you like a blanket, soft and warm. Thunderstorms have shaped human civilization in ways we rarely acknowledge. Ancient settlements were often located near regions with reliable rainfall, and thunderstorms were part of that life-giving cycle. The monsoon thunderstorms of Asia, the seasonal storms of Africa, the regular afternoon storms of tropical regions. All of these provided the water that allowed agriculture to flourish and communities to grow. Even our earliest calendars and religious observances were often timed to the seasonal arrival of storms and rain. The word thunder itself comes from the Old English word thuner, which was also the name of the Anglo-Saxon god of thunder, similar to the Norse god Thor. These deities were among the most important in ancient pantheons because they represented the power of storms. The power to bring both destruction and renewal, to frighten and to nourish. Language carries these old connections still. Lightning has been used by nature in unexpected ways. Forest fires started by lightning strikes, while sometimes devastating, play an important ecological role in many ecosystems. These fires clear underbrush, return nutrients to the soil, help certain seeds germinate, and create the patchy, diverse habitats that many species need. Some pine cones actually require the heat of fire to open and release their seeds. In this way, lightning doesn't just destroy, it renews. The study of thunderstorms has advanced tremendously in recent decades. Weather radar can now peer inside storms, showing meteorologists the internal structure, the rotation, the hail cores. Satellites monitor storms from space, tracking their development and movement. Lightning detection networks pinpoint every strike in real time. Yet despite all this technology, thunderstorms still surprise us, still show us new phenomena, still remind us that nature holds mysteries we're only beginning to understand. In the deep quiet of space, astronauts aboard the International Station have a unique view of thunderstorms below. From their vantage point 250 miles up, they can see entire storm systems, watch lightning illuminate clouds from within, observe the curved horizon as storms march across continents. They report that thunderstorms seen from above are among the most beautiful sights visible from space. Electrical storms pulsing with light against the darkened earth. There's comfort in knowing that right now, as you rest here, thunderstorms are happening somewhere. Over the Amazon, lightning flashes. Above the African savanna, rain falls. In the warm waters near Indonesia, new storms are building. The planet breathes, the atmosphere circulates, water rises and falls, and the ancient cycle continues as it has for billions of years, as it will for billions more. And you are part of this cycle too. The water in your body was once rain. The air you breathe has traveled through countless storms. You are made of the same elements that make up clouds and lightning, rain and thunder. You are connected to every storm that has ever been, every drop of rain that has ever fallen. So rest now deeply and completely. Let the storms of the world continue their work while you surrender to sleep. Let thunder roll on distant horizons while you drift in perfect peace. Let the rain fall gently on the earth while you sink into the softest dreams. The storm has told you its story. From the first rising updraft to the last falling drop. From ancient skies to this present moment. And now its final gift. The deep, restorative silence that follows, the peace that comes after the rain. Sleep well, dear listener. Sleep deeply. The storms will still be there tomorrow, painting the sky with light, singing their ancient songs. But tonight you rest. Good night.